All right, this is an exciting day in calculus because we are going to get into a really important topic called derivatives. So make sure your phones are put away out of sight so that you are not tempted to check them while you're watching the video. Take good notes. This isn't a super lengthy video, but I do want you to pay close attention to the demonstration we're going to do and what we're talking about here. So I want to start off by introducing what we mean by a derivative by looking at a function. And let's look at a function and see if we can get a visual representation of what we're talking about. I'm going to start off by looking at the function, and I'm just using the function f of x equals x squared as my example here. And my goal, my ultimate goal, is to calculate the slope of this function at the point 1, 1. So what do I mean by that exactly? Well, if it's a straight line function, the slope is easy. We just calculate the slope between 2 points. Remember the old formula for the slope between 2 points, change in y over change in x. Or you could think of as y2 minus y1 over x2 minus x1. Or if you're thinking about it in terms of f, you could say f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. All right, so that's something we've learned before. And if the function is a straight line, that's easy. That number you calculate is your slope. It doesn't even matter where you're at. But it gets a little more complicated when we're looking at functions that have curves and functions that change. So in calculus, we're going to look at what we mean by the slope of a function at a given point. What we really mean by that is the slope of the tangent line at that particular point. So if I think about the function 1, 1 here, I'm going to look at it as the slope of the tangent line that goes through the point 1, 1. Tangent line, you may remember the term tangent from maybe high school geometry, meant tangent to a circle, meant that it hit the circle at one point. And that's what I mean here. It's the line that hits that function at exactly the point 1, 1 only. So my question is, okay, how can I get the slope of that line? Well, one way to do this is to estimate it using another point on the graph. Now I'm going to switch over to Desmos here, and I want to show you what this looks like in Desmos using the same function. And as best you can, try to represent this or draw this in your figure, but watch what I'm doing in Desmos and make sure you can follow along with that. That's more important than what you have on your paper. Let's see how we do. All right, so I'm looking at the function f of x equals x squared, just your basic parabola in the first quadrant. 1, 1 was the point that I was interested in. So what I'm going to do, and by the way, here is the tangent line you can see in red. That's what I'm interested in doing, is estimating the slope of that line. So what I'm going to do is I'm going to choose another point on the function, on the graph. And I'm going to choose the point 3, 9. So in your picture, as best you can, label that point on the graph. And what I want to do is I want to estimate or try to approximate the slope of the line in red by calculating the slope of the line that contains the 2 points that I have on the graph, the 1, 1 and the 3, 9. So let's go back and do that. All right, so on the paper here, I am going to, let's see, I'm going to go ahead and try and label this, like I said, as best I can here. 3, 9, I'll put that way out here. And what I'm looking to do is to see if I can come up with a little estimate here for the slope of the line that connects, try to get it as best you can here. Let me see if I can get that a little straighter. The slope of the line that connects those 2 points. So if you have a straight edge and you can get it straight on your paper, go ahead and do that. All right, so how do I get the slope of that line? So I'm going to start, let's try to be organized about this on the paper. I want the slope. All right, so on my paper, I'm going to make a little chart here. I'm going to say x, and then let's do it this way. We'll say delta x, that'll be the difference in the x values, and then my slope. So at the point 3, 9, and 1, 1. That's what I'm doing. So I'm calculating the slope between these 2 points. Delta x, what I mean by that is the difference in the x value. So if I go from 1 to 3, the delta x would be 2. All right, so the slope, if I put this into this formula and I literally do f of 9, I'm sorry, hang on, f of 3 rather, minus f of 1 divided by 3 minus 1, that would give me 9 minus 1 divided by 3 minus 1, which gives me 8 over 2, which gives me a slope of 4. So let me go back to Desmos and let's look at a nicer picture of this. So that tangent line that passes through, I'm sorry, not tangent line, the line that passes through the point 1, 1 and 3, 9 is in green here, and the slope of that line is 4. That's what we just wrote down. Well, how good of an approximation is that? Not too great. You can see these lines are pretty slanted. This one's definitely a lot steeper, the one in green, than the line in red. That one's not quite as steep. So let's do it again, and let's choose another point that's a little bit closer. So let's try the point 2, 4. So there it is in the graph. And what I want to do this time is I want to estimate the slope of the original line, the tangent line, by calculating the slope between the points 1, 1 and 2, 4. So let me go back to my notes here. And just for space, I'm going to erase what I have. And I'm going to try as best I can to draw that line on my graph, although this may get a little bit messy, but let's see how we do. Let me find a different color here. So I'm looking for, I don't know, let's say 2, 4 is right there. I'm just kind of eyeballing it. And so I'm looking for the slope of the line that contains those 2 points right there. So on my paper, I'm doing 1, 1 and 2, 4. Notice that the delta x this time is only 1. What do I mean by that? That's the distance from 1 to 2, the difference in the x's. So my slope there would be 4 minus 1 divided by 2 minus 1, just using my regular old slope formula, and I get 3 over 1. So my slope there is 3. Let's go back to Desmos and take a look at that. And there it is. There is the line. Oh, wait a minute, that's the wrong one. Here it is. That's the line that I'm interested in, the one in blue. Let me zoom in a little bit. Notice that that line has a slope of 3. How good is my approximation? Remember, my goal was to find the slope of the line in red. It's a little better, but still not great. So what I'm going to do is I'm going to move the points a little closer together yet. So this time, I'm going to use the point 1.5, 2.25. So that's a point on the parabola. And what I want to do now is estimate the slope of the tangent line by calculating the slope of the line between those 2 points. So let me go back to my notes here. Let me make a little bit of space. And as best you can, again, on your paper, if you want to draw this, I know the graph is getting a little bit messy, so that's up to you. But I would be looking for the slope between 1 and, I said 1.5. I don't know, so maybe it's like right there. But let's look at the numbers. So we've got 1, 1 to 1.5, 2.25. These are just simply the y values when you plug in 1.5 into the function x squared. My delta x now is 0.5 because notice that would be 1.5 minus 1, the difference in the x's. So my slope is 2.25 minus 1 divided by 1.5 minus 1, which is going to just give me 1.25 divided by 0.5, and I believe that gives me 2.5 for my slope. So let's go back and let's put this together and see what that looks like. There it is. So the line in black is the line for the function, or rather the line containing the points 1.5, 2.25, and 1, 1. A little better. So the line in black now looks like it's maybe, if you looked at it from a distance far out, you could maybe say it looks parallel to the line in red. Pretty close, but you can see as we get close up, the approximation maybe isn't quite as good as we thought it might have been. So let's try this one more time. Let's move the points a little bit closer yet. So I'm going to get rid of that one, and I am going to look at 1.1. So now I'm going to look at the value where x is 1.1. So notice what I've done here is all of these x values that I was using, I made those x values get closer and closer together. So let's go back to our graph here in our notes. And my graph is getting very, very cluttered, so I don't know that this is all that useful to draw it here. But let's go ahead and let's put down on our paper what the slope would be. So we're talking about 1, 1 to 1.1, 1.21. Notice that the delta x, the difference in the x's, is now down to just 0.1. How am I getting that? That's the difference from here to here, here to here, here to here, and now down to here to here. So notice what's happening with these delta x's. The points were getting closer and closer together. So these x values, the delta x rather, are getting smaller and smaller and smaller. In fact, they're approaching 0, which we'll talk about in a minute. But let's look at our slope. My slope now is going to be 1.21 minus 1 divided by 1.1 minus 1, which gives me 2.1 as my estimate. So the idea, what I'm hoping you're observing, sort of, is that these numbers are getting closer and closer to a particular value, the slopes rather. The slopes are getting closer and closer to 2. That's the idea. So as those distances between the points got smaller and smaller, closer to 0, the slope values for those lines got closer and closer to 2. Let's take a look at what's happening here one more time in Desmos. And what I want you to see, it's a little hard to see because everything's kind of jumbled here. Maybe if I zoom out a little bit. The function, of course, was the parabola 1, 1, so the line in red was the one we were interested in. And the one we used to estimate it was between the slope of that point and the point 1.1, 1.21. So that line is in purple there. I actually think it's this one right here. Yeah, that's the line, I believe. And so you can see those are pretty close. They really are. And in reality, the slope of the real line, the one in red that we're interested in, is 2. So our final estimate of 2.1 was close. And if we had moved those points closer and closer together, we would have gotten slopes that were closer and closer to 2. So let's kind of summarize what we're talking about here. This is what we mean by a derivative. So a derivative is the slope of that tangent line at the point in question. And so the slope of the curve at the point in question, so we would call that a comma f of a, is given by this function. This limit is very important. We're going to use that for the next couple of days. This is called the limit definition of derivative. All right, what does all this mean? I'm going to pause the video, stand up, take a stretch break, and I want you to look at the second video in just a moment.